Welcome to Quantum. This channel is your gateway to the fascinating worlds of quantum mechanics, quantum gravity, and quantum philosophy, and everything in between. Whether you're a science enthusiast, a student, or an academic, we explore the mysteries of the quantum realm with depth, clarity, and thought-provoking insights. In our last episode, we delved into the core of symplectic geometry, discussing the symplectic form, Poisson brackets, Lie symmetries, and their role as a bridge between classical and quantum mechanics. We also explored Darboux theorem as the equivalence principle of quantization and the cotangent bundle's role in classical mechanics. In this episode, we'll take a step further into unifying Riemannian and symplectic geometries into the non-commutative geometry of complex projective spaces. We'll uncover how these frameworks connect and the profound implications for understanding quantum spacetime. Don't forget to like, subscribe, and hit the notification bell to stay updated. Let's unravel the quantum universe together. Comparison between Riemannian and symplectic geometries. Geometry provides the foundation for understanding the universe, from the structure of spacetime to the dynamics of physical systems. Two fundamental frameworks, Riemannian and symplectic geometries, offer distinct but complementary tools. Riemannian geometry, through its metric structure, measures distances, angles, and curvature, making it central to general relativity. Symplectic geometry, meanwhile, preserves areas in phase space, encoding the essence of classical and quantum mechanics. Although both geometries study smooth manifolds, their focus is fundamentally different. Riemannian geometry introduces a positive definite metric to study curvature, geodesics, and intrinsic distances. Symplectic geometry, on the other hand, uses a closed, non-degenerate two-form to describe the structure of phase spaces, essential for Hamiltonian dynamics. Furthermore, Riemannian geometry applies to manifolds of any dimension, while symplectic manifolds must be even-dimensional. Riemannian spaces measure lengths and angles, while symplectic spaces preserve area-like structures but lack metrics. Even their local properties differ. The local flatness theorem in Riemannian geometry guarantees that any point on a manifold can be locally approximated by flat Euclidean space. Symplectic geometry, by contrast, is governed by Darboux theorem, which states that every symplectic manifold can be locally transformed into a standard canonical form, independent of curvature. Manifolds that are both symplectic and Riemannian. Kähler manifolds unify Riemannian and symplectic geometries with a complex structure. These spaces satisfy compatibility conditions, making them ideal for studying geometry and physics simultaneously. Familiar examples include CPN, Calabi-Yau manifolds, and complex tori. In physics, Kähler manifolds are pivotal in string theory, where they describe compactifications of extra dimensions. Coadjoint orbits emerge from symplectic geometry and the action of Lie groups. They are symplectic spaces by construction, endowed with the Kirillov-Constant-Souriau form, and are essential in representation theory and geometric quantization. For example, the two-sphere is a coadjoint orbit of the rotation group SO3, while Grassmannians represent orbits of unitary groups. Homogeneous spaces generalize the idea of coadjoint orbits. These are spaces where a Lie group acts transitively, creating a uniform structure. While all coadjoint orbits are homogeneous spaces, the reverse is not true. Many homogeneous spaces lack the symplectic structure that defines coadjoint orbits. Bridging the two categories of Kähler manifolds and coadjoint orbits are moduli spaces. These spaces, which parameterize solutions to geometric or physical equations, often carry both Kähler and coadjoint properties. Moduli spaces of flat connections on Riemann surfaces, for instance, are symplectic by construction, but can also exhibit Kähler structures. Why CPN appears everywhere? Complex projective spaces, like CPN, are remarkable because they combine the properties of Kähler manifolds, coadjoint orbits, and homogeneous spaces. As Kähler manifolds, they bring together symplectic, Riemannian, and complex structures. This makes them key players in both mathematics and physics. CPN is also a coadjoint orbit of the unitary group SUN+1. Its symplectic structure arises naturally from the action of this group, while its homogeneous nature ensures symmetry and uniformity. Furthermore, as a homogeneous space, CPN can be written as the quotient of unitary groups, emphasizing its role in representation theory. This multifaceted identity, scalar, coadjoint, and homogeneous, explains why CPN appears in diverse areas, from algebraic geometry to quantum mechanics, and why it serves as a foundation for studying higher dimensional geometry. Spaces like CPN often appear also as moduli spaces in geometry and physics. In algebraic geometry, such quotients parameterize configurations of points or equivalence classes of vector bundles. For example, CPN can describe hyperplane configurations in projective space reduced by symmetry. In Twistor geometry, CPN represents a space of complex structures or moduli of self-dual geometries. Similarly, in gauge theory and sigma models, these spaces encode vacua or constrained solutions, providing insight into physical systems. This dual role, as both a geometric and physical moduli space, highlights the importance of constructions like CPN in bridging abstract geometry with real-world physics. CP3, a coadjoint orbit and Twistor space. Thus, CP3 is a scalar manifold and a coadjoint orbit. It also serves as a moduli space and a Twistor space. Moreover, it is both a Riemannian manifold and a symplectic manifold. CP3 stands out because of its unique role in both Twistor and non-commutative geometries. It can be understood as a fiber bundle over R4 in Twistor geometry or over S2 in non-commutative geometry. Both perspectives firmly connect CP3 to the four-dimensional structure of our universe. In Twistor geometry, CP3 encodes conformal and self-dual structures, linking it to quantum field theory and gravitational physics. In non-commutative geometry, CPN can be quantized as they are symplectic manifolds, leading to fuzzy CPN. Specifically, CP3 becomes a discrete space, and its fibration over S2 gives rise to a quantized version of S4, representing quantum spacetime. This is the only known approach to obtaining a non-commutative geometry of the four-sphere. CP3 in the perspectives of Twistor and non-commutative geometries. CP3, the three-dimensional complex projective space, is a key geometric structure that bridges classical and quantum worlds. It plays a pivotal role in both Twistor geometry and non-commutative geometry, revealing deep connections to quantum spacetime. In Twistor geometry, CP3 serves as the Twistor space of S4, encoding conformal and self-dual structures. Its fibration, where the fibers are two spheres, connects geometric structures on S4 to complex structures in CP3. This structure makes CP3 essential for understanding self-dual solutions in gravitational and Yang-Mills theories, linking it to quantum field theory and geometry. In non-commutative geometry, CP3 transforms into a fuzzy space. Fuzzy CP3 replaces the smooth functions on CP3 with a finite-dimensional matrix algebra, creating a discretized, non-commutative version of the space. This discrete version of CP3 serves as a fuzzy S2 bundle over fuzzy S4, a construction crucial because S4 does not directly admit a fuzzy geometry. The quantization of CP3 thus leads to a quantized S4, representing quantum spacetime. The fibration of CP3 also connects to the Kaluza-Klein mechanism, where higher dimensional modes along the S2 fibers are suppressed. This results in a low-energy effective geometry on S4, bridging higher dimensional theories with observable four-dimensional physics. This mechanism illustrates how CP3 links quantum field theory and higher dimensional physics with the discrete structure of spacetime. CP3 integrates naturally into matrix formulations of spacetime, such as IKKT-type models, which are non-perturbative approaches to string theory and quantum gravity. Its spin structure further makes it suitable for constructing models involving spinor fields and supersymmetry. The two perspectives, Twistor and non-commutative, converge in CP3. Twistor geometry provides the framework for encoding four-dimensional structures, while non-commutative geometry discretizes these structures, offering finite-dimensional models of quantum spacetime. Conclusion. CP3 unites two profound frameworks, Twistor geometry and non-commutative geometry. In Twistor theory, it encodes four-dimensional physics through its self-dual structures. In non-commutative geometry, its quantization discretizes space, providing a pathway to understanding quantum geometry. Through CP3, we witness a unification of Kähler, Coadjoint, moduli, and homogeneous geometries. It bridges Riemannian and Symplectic geometries, connecting the classical and quantum worlds. Its unique role in both Twistor and non-commutative frameworks firmly establishes CP3 as a cornerstone in the study of quantum spacetime. Thank you for joining me on this exploration. Don't forget to like, subscribe, and hit the notification bell for more deep dives into the quantum universe. Until next time, let's keep unraveling the mysteries of the quantum world together.